All right. I guess those of you who 15 or 16 wanted to show up in person didn't mean Fridays, because we'll have a few people here. So what we'll do is we'll kind of cover the Poisson distribution today, finish that new material, and then should have a little bit of time. We'll only be able to go over a couple questions on the practice exam. But then Monday, it's class. We'll just, whatever questions you guys have, we'll be going through those, bring those questions to class Monday from the practice exams, or really anything. And that'll be kind of our last review. And then the exam should show up under the, should show up under this quiz tab. All right, but it'll show up as kind of an exam, so you don't have to worry about that. You should be able to see that it clearly have it labeled as the exam, and so that'll show up Monday morning. Hopefully, before any of you have to wake up, it'll be very early. You could get on at any point during the day. Take it Monday. I would think most of you would want to wait until after we do the review, or you can get on any point during the day Tuesday and take it prior to 10:40 because it has to be submitted by midnight. And once you start, you'll have 80 minutes to complete it, right? Or an hour and 20 minutes, okay? You should be able to kind of, you'll have your formula sheets or, whatever materials you want in front of you. So I might have made it a little bit more difficult than maybe in the past, but I don't think it's too bad. It's 19 multiple choice questions with a 20th kind of bonus question that kind of, just can add points. So the total on the quiz will be 105, but it's only going to be graded out of 100, right? And there'll also be a short answer or question at the very end that has 4 different parts to it. And so that'll be kind of the composition of what it looks like. And that short answer, I think we already talked about, you can upload a picture of your work. You can upload, a Word document where you typed out, your work, but I need you to show your work. Excuse me. So it won't just be simply kind of the answer. I need you to show the work of how you got the answer. What form you want to do that in, whether or not it's a photo of your work, whether or not it's something, if you can scan something real quick, type out what you're doing in Word, upload your Excel file, all of that is fine, okay?
For the last question.
Just on the last one, yeah. Yep. It's like the last little short answer question. All the rest will be multiple choice, okay?
Don't have to show us anything else.
Nope, just that last one, yep. It's a good question. Okay, oh, the other thing I wanted to mention was, if we go to this playlist, I uploaded a few kind of videos of me working through practice problems. So, if you have specific questions on a problem, these are smaller, so it's a little bit easier to find, like where's problem 1, 2, 3, or 4. And it's just me working through, showing you how I would work through and solve these problems, right? So there's some that someone from that practice exam A, obviously 10 through 16 that aren't up here yet. I imagine we'll have kind of worked through all of those by today or kind of on Monday. I may even get up another little video or two this weekend. I'll be running around a lot today and tomorrow, but if I have some time, I'll get a couple of those up Sunday as well as you're kind of going through those practice exams if you get stuck on any specific question. Okay? All right. So we left off here. Any questions for me before we kind of jump into things? Good with that? Okay. So I can't remember how much of this I introduced, but we talked about the binomial distribution last class. So another specific discrete random variable we can talk about is the Poisson, right? So the Poisson is going to kind of fit these examples where we don't have a total number. We're not kind of capped out, right? It's just going to be the interval over length of time. You're all right. So it's going to be, we have some space, right? Usually this is going to be a time interval, but I'll give an example or two where it could be a physical space as well, right? So every equally length interval, so this interval might be like over the next hour, right? So the probability that we see something occur in the first hour is going to be the same as in the second and the third and so on and so forth, right? So equally length intervals have the same kind of probability of occurrence. We're also going to assume that they're independent, that there's kind of no overlap, independence in these non-overlapping intervals. So the first hour is independent from the second hour. So the setup is going to be that we want to know how many events do we typically see over this time interval, right? So this could be something like, you know, there's on average 10 accidents on McGalliard. I might be interested in the probability that I see 5 occur next week, right? Well, how many accidents can occur on Galliard? I don't really know what the cap is, right? I don't really know what the total number would be. I'd have to, I guess, somehow figure out how many cars are on the road, right? But I'm not given kind of what this total number I could see is. I just have I'm looking for the number of occurrences over an interval. So it's slightly different than the binomial. So just like the binomial, we had a probability mass function to find the probability of any one number of occurrences. We have the same thing for our Poisson, right? It's just going to be a slightly different equation. And I think it's easier, right? So if I told you on average there's 10 accidents on McGalliard, that's what we're going to say is our lambda, right? So this Greek letter here is lambda. It's going to be the usual number of occurrences we see, or the mean number of occurrences we typically see. X is then going to be the number of occurrences I want to find the probability of happening in the future, right? So maybe on average there's 10 accidents that occur each week, that's lambda, and I want to find what's the probability that there are 5 next week. So that would be my X. The only other thing in this equation that we don't know or might not know is E. E is just this natural number, kind of like pi. If we took it out to the fifth decimal, it's 2.71828. It should be on almost every calculator. Usually you have to hit like the second button, and it's above one of the other buttons, so it's kind of written there, and usually in
like above log.
yeah, usually it's like second log, or depends on what your calculator is, but usually that's where it's at. So it should be like written somewhere on there, you can see it. If you can't find that on the calculator you plan on using in the exam, let me know. I'll try to help you find it. Or if you panic, I don't know, couldn't find it, you used to know where it was once you get the exam, you can always use this number of 2.71828. Way I always remember it's like 271828. Now we have everything in this equation we know, or we need to know. We know factorials from the binomial, so we should be okay with that. Remember, 5 factorial is just 5 times 4 times 3 times 2 times 1. And now we can find the probability that we see a certain number of events occur over whatever that given interval that we want it is. Could be a week, could be an hour, whatever it is. Right? So let's work through an actual example with some numbers just to kind of put a little more context to this. So there's this, I'm not even going to try to say this guy's name, but real smart guy, wrote a really kind of pivotal book in mathematics, statistics. And one example that kind of he was using was that on average, the Prussian cavalry, saw 0.61 soldiers die every year by getting kicked to death by a horse, right? So over the time interval of a year, the mean number of soldiers that were dying from this was 0.61. Okay. Now remember, we're still dealing with a discrete random variable. So if 0.61 is my mean, what would be the most likely outcomes I could see? What would be the most likely outcomes I see occur? So just like with a binomial, if it's not an integer value, which this is not, the most likely outcomes would be we see 0 and 1. Those will have kind of the 2 highest probabilities of occurring. And then as we move further from that mean, right, the probabilities will start to decline. And so like the probability that I see, 10 soldiers killed by horses in the next year, really, really low, right, if the average is 0.61. Okay. So if I wanted to find what's the probability that exactly 3 are killed next year, well, the average is 0.61, so 3 seems a little high, but we could figure out what that probability is. Right? Here's our lambda, here's our x. Once we have those 2 components, it's really just like the binomial. You just plug them into that probability mass function. So everywhere there's a lambda, we plug in 0.61. Everywhere there's an x, we plug in a 3. Now it's a matter of getting this entered into our calculator. Now don't forget, so this is e to the power of the negative lambda, so negative 0.61. If you don't include that negative sign, you will get wildly incorrect answers. In fact, usually they'll be actually above 1, which doesn't make any sense because we're looking for a probability. So make sure you don't forget this negative sign. Okay. But once we have everything plugged in, it's just a matter of plugging away, right? Plugging into our calculator, we get about 0.02. So if on average 0.61 soldiers were killed every year, the probability we see 3 killed next year is only like a 2% chance that that happens, right? A probability of 0.02. Okay? Any questions on that before we keep moving? I mean, the process is really the same as what we were doing with the binomial. It's just now we don't have to, we're given what the mean number of occurrences is, lambda. We know that, x is something we're going to kind of be told or we're going to choose. And once we have those two things, it's just a matter of plugging them into that probability mass function, which I would argue this is a lot easier than that binomial equation. Okay? Not near as many factorials, not as many components to worry about. Okay, so what if I had a different example? I've got a hospital. They're kind of thinking about, we need to make sure we always have enough people on staff for kind of deliveries. And the average birth rate we typically see in an hour is 1.25, right? So what would be the probability that exactly 3 births occur in this next hour? Right? Well, if the average rate is 1.25, that's our lambda. The probability we see 3 the next hour, that's what the x we're interested in. So x is 3, lambda is 1.25. It's really just a matter of plugging those into our equation and getting comfortable kind of using this equation in our calculator, right? That's how we identify kind of our lambda or x. So lambda always has to be given to us. And then x is usually like what I'm interested in finding the probability of, right? Here, exactly 3 births per hour. Now, if my mean or my average number of births I typically see over an hour is 1.25 here, what are going to be the most likely outcomes that I see? 1 and 2, right? Still discrete random variable, so we can't see 1.25, but we could see 1 and we could see 2. So 1 and 2 should have the highest probabilities of occurring. Kind of 3 will start to decline, but it's hard to say how low it'll be. There's nothing we can really rule out here as an answer. It's just a matter of plugging it away, and we find that it's about probably a 0.09 or a 9% chance that there are 3 births. So if I'm making like staffing decisions at the hospital, I want to make sure, if it's a 9% chance, that seems to me relatively, high. It's not very unlikely. I want to probably make sure I have enough people to be able to cover those three deliveries, right? Okay. We'll then kind of make this a little bit harder, but this is things that we've already seen with the binomial distribution. So let's say I have that same average rate of 1.25 every hour, but now I want the probability of 2 births or more. So 2 or more births. So what I'm going to think about here is, what I'm looking for is the probability that x is greater than or equal to 2. Okay. Now this is very similar to the binomial, where I'll find every single outcome that fits this criteria and add up all the probabilities of those outcomes. But what's the problem here if I do that? So this would be the probability that x is equal to 2, plus the probability x is equal to 3, plus the probability x is equal. Where do I stop? Right? It's not a binomial example. I don't have this total number of trials that I know that I'll end at. So just like with a binomial, we can use that complement rule trick, where I know that if I want the probability of an event, it's going to be equal to 1 minus its complement. Right? So if A is that x is greater than or equal to 2, what would A complement be? Not equal, just less than, right? We need to be careful with that equality. The complement, right, if the equality is already here, it wouldn't be here. Up. So the probability that x is less than 2, and so now we can think about, what are the outcomes that fit this criteria? X being less than 2, the very first outcome that fits that criteria would be, x is equal to 1. And then the second one would be probably x is equal to 0. Yep.
Would we ever get into negative?
Well, remember, so we're dealing with the number of occurrences. So at the very least, we're always going to be 0. Yep. So the Poisson and binomial, because we're dealing with the number of occurrences, we could never see a negative value. Yep. For like a regular discrete random variable, you could see negative values though. Okay. So we've got 1 minus these 2 probabilities. To find each one of these probabilities, we'll have to use that Poisson equation. One time, we'll use it and plug in x is equal to 1. Another time we'll use it, plug in x is equal to 0. So if we go ahead and do that, right, here's that Poisson equation using that average rate of 1.25 when x is 0. Here's the same thing when x is equal to 1. So we have these two probabilities. We need to add them up, right, and subtract them from 1. So 1 minus those two, we get about what, 0.355. Okay. So, one thing you want to make sure when you're working on these that you don't forget to do is, like, it's very easy to add these up and then forget to subtract from 1. But if we think about here, like, if I wanted the probability that x is greater than or equal to 2, it doesn't include the most likely outcome of 1. So, if I add these up, it's like, what, 0.65? That probably seems a little high for not including the most common outcome of 1. And in other examples, it'll be a little bit more obvious. I'll kind of point that out. But this is how we would approach that Poisson example where we use that complement rule. Okay. Any questions on this one before we keep moving? Okay with that? Okay. We have different Poisson distributions here. As the mean gets higher, you kind of notice this becomes like less and less, I guess, right skewed. I'm going to use this for something else I'm going to talk about in a second. But this is just kind of a nice visualization as that mean rate gets higher, our kind of distribution starts shifting to the right a little bit. Now, what ends up being true for the Poisson has some really unique characteristic. Well, the mean, that's kind of easy. That's what we're given, right? We know the mean rate we usually see over that interval. So the mean is just lambda. Right? We're always given that. But the variance actually also ends up being lambda. If we looked at kind of this mathematical proof, it always works out that for a Poisson distribution, the variance will be the average rate, or will be lambda as well. Excuse me. And if we wanted a standard deviation, as always, we would just take the square root of the variance. Okay? So that's not too tough. Says, yeah, nice kind of property there. So if we go back to the binomial for a second, I want to relate the binomial to the Poisson. Okay? I might not ask you to necessarily do this approximation on the exam, but this gives us two good examples we can work through, one with a binomial and a Poisson. So let's say I've got, 10,000 atoms of some radioactive substance. The probability that any one atom decays is 0.0005. What's the probability that exactly 3 atoms decay in a given minute? Okay. Well, we either see an atom decay or we don't. So that's a success failure. It's a binomial example. The highest number, right, the number of atoms that we have, the number of trials would be 10,000. And the probability that any one atom decays is 0.0005. We've got n, x, and p. We can plug that into our binomial formula. So if we go back, plug those numbers into our binomial probability mass function, we could find the probability x is equal to 3. Now, I can't put 10,000 factorial into my calculator. That's just not a thing. But here we could see, after 9,997, everything would cancel, right? But it's kind of a pain to deal with those factorials. If x gets a little bit higher, I might still have a really, really large number that I'm dealing with. So what's one way, if I try to do the intermediate calculations and not enter all this, if I do 0.005 to the third, that's like becomes a really small number. So if I'm breaking this down into parts, it's kind of a pain to deal with. But if I do it, I can get the answer, right? But it's annoying. So if we have a really, really high number of trials and we've got a really, really low probability of success, we can actually approximate the binomial distribution with the Poisson. And what we're going to do is we're going to say, okay, we're going to set lambda equal to whatever the mean of the binomial is, right? So whatever the mean of that binomial distribution is, we're going to treat that as though it's the mean from a Poisson distribution and be able to get a really close approximation to what the probability that x is equal to 3 is. So here, 10,000 times 0.0005, that'd be the mean of our binomial, right? Because that was just n times p. So that would be 5. So we're going to treat 5 as our lambda, plug into lambda 5, that mean. We're interested in finding the probability of 3 atoms decaying, so x is 3. So if we plug those values in, we actually end up getting the exact same thing. Well, out to the 5th decimal. right? If we keep going out 6th, 7th, 8th decimal, it's a little bit off, but it's a very, very close approximation and a lot easier to deal with, right? So this is kind of a, and here we were looking at atoms decaying over a minute. So we did have a time interval. We can kind of convert this binomial distribution into a Poisson example and get a really close approximation, even out to the 5th decimal here, okay? Any questions on that before we keep moving? And a nice visual of this is, here, let me exit this so I can. So notice here, we had a Poisson with a mean of 0.5. The probability that x is equal to 0 is about 0.6. Probability x is equal to 1 is about 0.3. And then it kind of falls off pretty quick, right? Well, even with, if we go back up to the binomial, a binomial that has a mean of 5, right? And here, n times p would be, sorry, a binomial that has a mean of 0.5. So here, n times p, 5 times 0.1 would be 0.5. Notice the probability that 0 occurs for the binomial is also close to 0.6. Probability that C1 is also close to 0.3, and it falls off pretty quickly afterwards. Now, here, n and p, n is not really large and p is not really small. So these aren't going to be exactly the same. But even with small n size and not the smallest probability of success, a Poisson and a binomial with the same mean look have very similar distributions. But in order to be able to truly use the approximation, we should have a really high number of trials and a really low probability of success. Okay. So I'm going to walk through these scenarios and just give you a couple of ideas of what look like a Poisson and what don't. So I've already kind of used this one as an example, but if I want to know the probability a certain number of accidents occur on a highway in an entire day, if I can find what the average rate was in the past, that's, the number of accidents or my number of occurrences, got a time interval of a day, that'd be pretty easy. What about the probability that a stock return exceeds 10% in a given year? Well, I might see this initially and think, okay, yeah, over the time interval of a year, but what am I looking for the number of occurrences of? This is wanting to find the probability that a stock exceeds 10%. Well, it can't, if I'm looking at this year, it can't exceed 10% 5 times that year if I'm looking at the return from that year. So this is going to be one where we can't find the number of occurrences. It's not going to be a Poisson scenario. Right? And then the other two, the probability a certain number of calls come into a call center. It's pretty easy if we had past data on how many calls typically or on average come in every minute. Probably a certain number of insurance claims come in over whatever period of time, a year, a month, a day. And these are really relevant, very apt. We can definitely apply the Poisson. It applies to a lot of different scenarios that you could see it being used for. Right? I might want to know the probability that I get 100 phone calls, because if I get 100 phone calls, I don't have enough people to be able to answer all of them. I might want to know the probability that I see 20 claims, because if I get 20 claims come in the next month, I don't have enough. I don't have kind of enough people sitting around to be able to manage all that, or I don't have enough money sitting there to be able to pay out everything. And so if the probabilities are relatively high, I might be concerned, right? So these are all, the Poisson is just pretty applicable and kind of can think about, there's a lot of scenarios where we can use it. So I'm going to go through one more example here in the slides and then an example here up here on the board. So there's this guy, W.S. Gassett. He was a really smart guy, but he started working out as a brewer for Guinness. He had no real education in statistics or mathematics, but as he was testing if you ever been to a brewery or anything where they brew this beer, you have these huge vats of where they brew this beer. You obviously can't test the entire who knows how many gallons of liquid to make sure that it's brewing the way you want, but you can test milliliters or a little bit of it at a time. Yeah. No. This is just me trying to set up to not be too completely boring, right? No, you would never know these people's names. So as he's kind of testing these, milliliters of liquid from this huge vat, he notices as he starts to record them and track them, it follows a Poisson distribution, right? Which kind of led him to discovering some other distributions. But because he didn't have a degree, they didn't name the distributions after him, so we call them student distributions, as opposed to the normal distribution is called Gaussian because some guy named Gauss came up with it. We kind of set this up. So as he's testing these milliliters of liquid, he noticed it follows a Poisson distribution, right? And he made a bunch of money. So let's say for this example that after he tests, I don't know, 100 different times a milliliter, 100 different milliliters, and records the yeast particles per milliliter to kind of make sure it's exactly where they want it so that the beer tastes the way that they want it to taste. And he finds that over those 100 samples, the average is about 10. On average, when he tests one of these little milliliters of liquid, he sees 10 yeast particles per milliliter. Well, we're not dealing with a time interval now, and on the exam, I wouldn't give you anything other than a time interval, but we can use the Poisson on space intervals as well. And it's kind of weird to think about, like here, a milliliter is like, that's the space we're looking at, as opposed to a year of, like, we're looking at a milliliter, right? And so we're still looking for the number of occurrences over that interval, the number of yeast particles we see. And so if on average we see 10, that's our lambda, and I want to find what's the probability that I see exactly 8, well, that's what I'm interested in finding the probability of, so x is equal to 8, right? I can then plug these into my Poisson and get that probability. Because the average is 10, but any one sample I take, I could see 9, I could see 11, right? And I might want to know what's the probability I see those different values, okay? Specifically, if I know what I want this to be ahead of time, if I had like a sample that had a little bit lower, I'm like, well, it's okay. The whole vat of liquid still could have this average of 10, even though when I took out a sample, I saw 9 because, 9 is a fairly likely outcome for me to see, okay? But if I saw something like 3, well, if the average is 10, there's no way I should have seen 3. And so I probably have something wrong with my process, my brewing process. So if I've got my lambda as 10, that's the average or the mean that we usually see. And I want to find the probability that's equal to 8 in this one little milliliter of a sample I take. Which of these can I rule out as a possible answer? And I can plug these into the equation and get the answer, but I can rule one of these out. So if 10 is the mean, it should also be the most likely outcome or have the highest probability of occurring. So if the probability of seeing 8 was in fact 0.83, I only have like 0.17 of probability left that I could even assign to the probability of 10. And so that would make 10 not the most likely outcome, right? I mean, if the probability of seeing 8 was 8.8, there's no way the probability of seeing 10 could be higher than that. But I know because 10 is the mean or 10 is lambda, that it has to be the most likely or have the highest probability of occurring. So right away, if I look at any value other than this expected value or the mean, I know, or lambda, I know that this probably has to be less than 0.5. So I could rule C out right away, but from there, it's really just a matter of, I've got lambda as 10, I've got X as 8, just plug and chug away because it's beer. That was pretty bad. So I plug in lambda, I plug in X, right? And then it's just like every other example we've been doing, okay? Any questions on that one? Okay with that? All right. And then this is always a great, when you're talking about the Poisson, right? If you heard the joke about the Poisson distribution, it's pretty fishy because Poisson means fish in French. It's just another terrible statistics meme. Okay, so we got actually way more time than I thought. So let's go through. I want to work through something else that we could do with the Poisson. And you could see wink, wink on your exam, right? So let's say that the number of people, struck by lightning every year is 36. Right? Well, if I asked you what's the probability that 30 people are struck by lightning this year, you've got lambda, you would have your X, kind of like what we've been doing. But what if I ask you for the probability that, let me think about what I want here. Let's think about the probability that this next month you see 2 people struck by lightning. Well, I can't use this as my lambda anymore because I don't have the same time interval. But if I'm also told, and I don't know if this is scientifically correct, but for my example, let's assume it is, that it's equally as likely to be struck by lightning in any month if you're standing outside. Then how could I convert the average of a year to be the average over a month? Yeah, just divide by 12, right? So 36 divided by 12, or 3. I've now got my new lambda. It's in the same time interval as what I'm interested in finding the probability of. Lambda is 3, x is 2. Plug them into our Poisson, and it just kind of, from there, it's just using our calculator. So anytime we want to, we sometimes can be given information in a longer time interval than we want. If we want to shorten that time interval, we always kind of divide by whatever that conversion factor is. And on the exam, if I ask you a question like this, it's going to be going from a year to month. It's going to be going from a week to days, right? So there I divide by 7. Maybe a day to hours, so I would divide by 24, right? It's going to be something that I assume that's common knowledge. I'm not going to throw a non-time example at you and say, how many, I'm going to go from miles to yards, right? I'm not going to do something like that where you might not remember it off the top of your head. So pretty easy conversion. So anytime I want to go to a smaller time period, I divide by my conversion factor. What if, we'll do in here. What if instead I said, what's the probability over the next 2 years? I don't know. 50 people were struck by lightning. Well, if I have the average over a year, what would the average be over 2 years? Just 36 times 2, right? And so if I ever want to go to a larger time interval, all I do is multiply by whatever my conversion factor is. Now here, this is a weird one. I went from year to 2 years. It's just doubling it. But what if I would have went from, say, a day to a week? I would have just multiplied it by 7. Yep. And then once I have the correct lambda, now it's just a matter of plugging lambda and x into that Poisson equation. Okay? So I'm not working all of these out to get the exact probabilities. I'm just giving you an example of if we wanted to do these conversions. First, I have to find the correct kind of lambda that's in the same time interval. But once I have that, now it's just kind of like we were doing in all the other examples, plug them into that Poisson equation. Okay? Any questions on this before we keep moving? We're okay with that? Excuse me. All right. Got a little bit of time here. I'm going to work through a couple examples. So let's start off on practice exam A. And we'll start on problem 10, okay? So we're given some information here, right, about whether or not people are lying and lie detector results. So suppose that given someone is lying, the probability that lie detector says they're lying is 90%. So anytime we have questions like this, I think that the best way to approach this is write out what we're being given, okay? I'm going to see if I can, hopefully the recording of this will look okay. I'll get this as big as I can, just so I can start to identify what we have, okay? So the very first thing we're told is the probability that, given someone is lying, right? So the given is what comes on the right-hand side of that vertical line we're writing out probabilities, right? So given, right, and just to make sure, because the L kind of looks like this, given that someone's lying, the probability of the lie detector test says they're lying. So LD, I'm just going to use a shorthand for kind of the lie detector result. We're told that probability is, so it's 90%, so a probability of 0.9. I then have the probability, the next one is, however, given that an individual is not lying, so given, instead of not lying here, I'm going to write that they're telling the truth, but not lying, truth. Given they're not lying, the lie detector incorrectly determines that they are, in fact, lying 20% of the time, or a probability of 0.2. Okay? I'm then told recent studies find on average people lie about 5% of things they say. So the probability someone's lying is 0.05, right? That's all the information we were given right here for these next three problems, okay? So what's the probability that a person is lying and the test says they're telling the truth? Okay. Let me see a group here. So what are we looking for? So we've got all this information, right? And what we're looking for is the probability that someone is what? Lying and the lie detector test says they're telling the truth, right? That's problem 10. So I've just written out the probability, like what we're looking for, okay? Now I'm gonna have to erase this, but if we have this written down, is everybody okay if I erase this? So this would be like at the top of my page, all right? If I'm looking for the intersection of two events, and I go to, where is it? It's hiding. I go to my formula sheet, and I want the intersection of two events. I can rewrite that as the conditional probability times what I'm conditioning on. So A and B, I can find the probability of B given A times the probability of A. So I'm just going to use that formula and write out, right, as a reminder, it's going to rewrite my intersection as a conditional probability divided, or sorry, my conditional probability times what I'm conditioning on, okay? So make this a little bit bigger for the video. But if this was my A and this was my B, the formula sheet said to take B, so the probability lie detector test says they're telling the truth. Rewrite that as given A, so the probability that they're lying. And then multiply that by the probability of whatever I'm conditioning on, which is that they're lying. Okay? So all I did there was write down what I'm looking for. I then went to my formula sheet. See, I can rewrite an intersection as a conditional times what I'm conditioning on. Once I had that formula, I then just wrote that out in the context of my example, right? So the general form in the formula sheet looked like this. So I just plugged my B in, plugged my A in. Now that I have this, I go back to what I was originally given. We had written down the probability of lying was 0.05. And we had that given that someone is lying, but probably the lie detector test says they're telling the truth. I don't think we were actually given that, right? What we were given was given that someone is lying. The probability the lie detector test says they're lying was 0.9, right? But if I know someone's lying, right? That's what I'm given. I know someone's lying. And the probability the lie detector test says they're lying is 0.9. Then the probability that lie detector test says they're telling the truth would just be 0.1, right? There's only two outcomes for this test. And so if I'm conditioning on the same state of nature, those conditional probability of those two outcomes have to add up to 1, right? And so this was one where, we could do those probability trees if that helped you kind of think about that in an easier way. I'll probably work through another one on Monday, another Bayes theorem. But we condition on the same state of nature. Let me just make sure that these are my conditional lines. The two different outcomes of the test, those would have to add up to 1, so we know this would be 0.1. So we plug those values in. 0.1 times 0.05 should just be 0.005. Okay, I'm going to skip 11. It's very similar to how you would do 10. I'm going to go over 12 because I think it's a little bit more difficult. Also, let's make sure this. Yeah, this is practice examiner. So given an individual fails the lie detector test, what's the probability that they're actually telling the truth? So once again, I think the first place to start out is, what am I looking for? So I'm told, given that someone fails the lie detector test, so given that the lie detector test says that they're lying, what's the probability that they're actually telling the truth? I think that's what it is. Yep. So what's the probability that they're actually telling the truth? Okay. Now, I wasn't given this probability directly. If we look back at those first three things written down, I didn't have that, right? But what I did have was this formula sheet. And if I try to look at a conditional probability, I can rewrite it as the intersection divided by what I'm conditioning on. But in our example, our event B is that the lie detector test says someone's lying. So to have just the probability the lie detector test says someone's lying, I don't have that. I have the conditional probabilities, but I don't have the unconditional. So if I try using this formula, it's not going to work. But we can break that formula down into kind of Bayes' equation, right? So this is going to be the one where once I have written down the probability I'm looking for, if it's a conditional probability, pretty good likelihood that if it, I was given a bunch of information ahead of it, probably going to have to use, you can kind of notice the practice exams have a very similar format. And so probably a pretty good example, I'm going to have to use Bayes' equation here. But once I have this, I think about, okay, I need to identify my S and my E. So here's my S, here's my E, right? I would even just, oh, I just noticed this kind of isn't on there. Right, here's my S and here's my E. So I'm just going to write out this formula in the context of my example, okay? So what is my S? Well, my S is that they're telling the truth. So I'm going to take the probability that someone's telling the truth, multiply that by the probability of E given S. So my E is that the lie detector test says they're lying, given S is that they're telling the truth, right? And then I'm going to divide this by, right? So I'm going to divide this by, notice the first part of this denominator is the exact same thing as the numerator, okay? So I would write that down again. Well, I can try to make it, it's going to be small so I save myself enough room. But you can imagine it's just the exact same thing as the numerator, okay? So I know it's a little bit small here, but what you have in the numerator will be what's down here in the denominator, okay? The second part of that denominator is the probability of S complement. Well, if our S is that they're telling the truth, our S complement would just be that they're lying, right? And then multiplied by the probability of E given S complement. E was that the lie detector test said they're lying. Given S complement, that was just the probability that they were lying, right? So I now have this equation written out in the context of my example. So just to kind of make this a little bit bigger for those of you who watch the video afterwards, right? I now have Bayes kind of equation written out in the context of my example, and I can start plugging things in. If I go back to those first three things that I originally wrote down, what was the probability that somebody was lying? 0.05. The probability they were telling the truth, we had, didn't directly have that written down, but right, if I know the probability someone's lying is 0.05, probably they're not lying or telling the truth is 0.95. We had all these conditional probabilities written down as well. So just remind me, given that they were telling the truth, what was the probability the lie detector test incorrectly said they were lying? Are any of you writing this down with me? It was like 20%. Yeah, we had that written down as 0.2. And then given that they were lying, probably the lie detector test said they're lying, I think was it 0.9 we had written down? And now I've got a bunch of numbers. It's just multiplication, addition, division, making sure I do my order of operations correctly, right? So write down the probability of what you're looking for, then put an S and an E over it. Then go to your formula sheet, write out Bayes' equation, substituting in for S and E, whatever your S and E are. And then if you had written those first three probabilities down from the information given in the problem, well, now it's just a matter of plugging those things in where they belong, right? Any questions on that? I think this is probably one of the harder questions on, maybe the hardest question on the exam is these Bayes ones, just because it's a lot of information you're given that you have to write out the probabilities. I don't know. I just think for whatever reason, it tends to be the one that people have the most difficulty with. So if you're wanting more practice on it, right, first of all, what we did here in class today, I'm going to cut up part of the lecture into a little video so people can kind of see me work through these two questions. But also going back on YouTube to, I'm going to get myself out of the way here. This additional Bayes recording, I worked through, I think, 2 examples in that a little bit more thoroughly. Notice, I mean, it's 20 minutes. I'm only kind of working through 2. I'm going through a couple different questions that I could ask you on it. I think that would be a good thing to review, just for more questions with that. Also, like the examples that I use, like wink, wink, would be really good ones to go over before you do the exam. So if you want more practice with those Bayes equations, I would kind of watch this and try to work through maybe, just watch me set the problem up and ask the probability, and then you try to kind of work it out and make sure you can follow along with what I'm doing. Okay?
Is the YouTube channel linked on Canvas?
I don't have, I think like the very first week there's yeah, it's in like, there's also, I think I have it in this, there's a point in the syllabus that's there, I think in the first set of slides. But the easiest way to do it, God's honest, is like go to YouTube, search Professor Lannis. That's probably the easiest way to find it. And then from there, go to playlists, and I've got my 3 sections. Honestly, 3 and 5, a lot of those will look really similar. I mean, it's different lectures, but the video, like additional Bayes, will be the same. Click on your section. Should be kind of all ordered from in a chronological timeline. But yeah, the easiest way is just Google search Professor Lannis. That's how I find it. So yeah. Any other, we got a couple minutes. If there's any other questions or anything before we get out of here, we're okay. All right, so we'll be doing a whole class of review on Monday. The way it'll be most beneficial is if you ask me specific questions. Otherwise, I'm just kind of picking and choosing what I think would be important. Okay. All right. Have a good weekend. I will see you Monday.